Hi, we're Team ZetaCubed. This is our senior design final presentation. I'm Alex Blakely.
I'm Austin Piper.
And I'm Finley Butler.
For our project, we were provided our project by Intel Corporation. They desire a way to open a server in a more efficient way and allow routine maintenance to go easier and less work for the maintenance people, preferably a spring-loaded hinge that is force and vibration dampening while closing. The requirements for our hinge, we found the hinge must overcome a 5.71 Newton moment arm. And we are going to do this many times, so we have to consider cyclic loading. The prototype should be scalable and easily reproduced for different needs. And the cost and scale should be unique to our product itself.
So some of the codes and standards we used, the first one was ISO 9000. We're using that for quality assurance. And we're going to be using we use a lot of product validation and product verification to make sure it met high standards that we had. Since we're using cyclic loading, like Austin said, we're going to be using the Goodman's approach for fatigue loading. And since we're using actual stock springs instead of manufactured ones we're doing ourselves, we're going to be adhering to ASTM standards. And we are also using ANSI requirements for data centers, and that basically covers servers. So these are some of our initial designs that we created. Each one of us created one of them, and we eventually decided to combine what we liked the most about each one of these designs into the one we would end up doing for our final prototype. And these were some of our preliminary drawings at our mid-semester last year. And as you can see, the hinge we initially envisioned to be an enclosed system because we wanted to have viscous fluid inside of there. And a lot of this changed, especially the spring and the enclosed housing.
We decided to enlist a design for manufacturing and assembly approach. And what this did for us was it optimized time to market, and it also limited manufacturing production costs during prototyping, and it expedites that testing and prototyping phase. And it optimized our print assembly during our design. And after those initial drawings and going back to the drawing board, we decided to grow on those drawings and took some new points here. We discovered some flaws in our system, and we needed some more springs in there. You can see there in the yellow, the 3 springs to overcome the moment arm of the door. And we also optimized rod and dampening components there in the middle. And we used that design for manufacturing approach to really consider production in these designs.
So for the rod design, we tried to take the DFMA approach, like Finley said, and so we tried to make it as simple as possible. So we just made it a long cylinder. Also made it very easy to do the calculations for the design stress. And so taking the tensile stress, we were able to calculate the endurance limit, which would be 67.5 megapascals, which would greatly exceed the moment arm of the door that we're going to be overcoming, and they'll make sure that it wouldn't break and it would last the 10 to 20,000 cycles that we wanted. And the original rod that we had designed was on the left there, and we were going to make it out of SAE 1020 steel. It was a very strong steel. But after we tried to make it ourselves using a lathe, it was way too small. The diameter is about 8 millimeters, and the clamps couldn't hold it. So we decided to switch over to 3D printing, and we were going to do a nylon, but we ended up settling on PLA after a while.
For our spring, initially we wanted to design a custom spring just to employ our machine design knowledge that we've learned. And we started, and with our resources, we only had a few design stress charts to go off of, and our custom spring came up to be not physically possible just due to the calculations not turning out correctly. This resulted in us going to Dr. Washko and deciding on a stock spring from Lee Spring, and that spring is to have a max torque of 0.978 Newton meters. And these are the specifications for that spring.
And then one of the last things we decided for our initial prototype was to do a viscous fluid drag using those fins that are in the middle picture there. And we originally decided to use the bio chain oil. Basically, it was slightly more viscous than water. And after our calculations, we found that it would be about a drag of 1.18 kilograms. And that's on both halves of the fins there on the hinge. We ended up scrapping it though due to leaking, but this is how we designed it initially. And this was the evolution of the bracket design. And so the bottom left was our encased, and so that was only the top hinge. The bottom hinge would have fit evenly with those three, and it wouldn't work because we had no way for the springs to come out and actually like provide the torsion that we needed to open up the legs would have had to have been really small. And we also had trouble when we even decided to try to use the oil, that it would actually leak out, and there was no way to really do the print in place that we wanted to as well for 3D printing. So we eventually moved up to the top, which was much more spread apart, and then when it combined with the lower, which is the bottom right picture, we'd have space in the middle for all three of the springs that we wanted to have there. And so we went from the one on the right, like I said, which is fully encased, and then to our final one, which is on the left.
For design analysis, we created these preliminary mechatronics diagrams that we would be able to use to analyze our hinge setup. We had some issues with Inventor, and we reached out to Professor Davis for assistance in creating the springs in Inventor. Additionally, translated to slightly higher cost in manufacturing with some of the changes that we made for the design analysis. It just took more time 3D printing, and had some different angles that we were going to have to work on for the manufacturing side of things there. And all of this stuff had to be addressed prior to prototyping. Using that design for manufacturing approach, we wanted to address all of this stuff before we started to save time and money when we started testing there. This is our midterm production drawing. And as Alex mentioned earlier, the encasing around the springs was dropped. And you can see the 3 springs there. And those are the stock springs, like Austin had mentioned. We went away from the design springs just as they were infeasible. And so that's our midterm production drawing.
We used ANSYS to create some simulations on the structural stress and strain of our spring. And in the top picture, it shows it being done at a 90-degree angle because that's where the spring will be while it's closed. And on the bottom, it's showing it at 180 degrees in that first 35 degrees of movement. And both simulations result in much lower stresses and strains than what our materials can handle. Additionally, we did the same stress strain on the rod and conducted simulations to see the stress intensity and the elastic strain intensity. And again, our results were much lower than what we can withstand.
And for our design process, coming back from the break, we really had to familiarize ourselves with the manufacturing process of 3D printing. So this was all of our first times. And so we reached out to for some advice on that, but we ultimately decided on this because it was cheap, it was automated, and very easy to make changes to our design. And we made a lot of changes throughout this time. There's also a very large material selection available, anything from wood to carbon fiber and nylon, and we ultimately landed on PLA in the end. And like I said, we reached out for some advice and did our own research to come up with how to slice the slicing softwares to get the STL file into the G code that the 3D printer would read. And considering the design for manufacturing, we had to consider the orientation in 3D printing, and that was probably our original challenge, was figuring out how we're going to orient each component and optimize that.
So as Finley said, we used a highly iterative process to create our first physical prototype. You can see basically from left to right, we had all of our calculations to where like the thicknesses of the material, the way we had them, would work, but the printing wouldn't work because the tolerances were a little bit off from what we thought they would be, just due to inexperience with 3D printing. And so we went through probably a dozen different iterations, and then once we got the iterations, we had to learn about different types of when we tried to do design for menu or printing in place, we had to figure out orientations, as he also mentioned. And yeah, so as we got everything thicker, we also had to worry about the accuracy of the prints because we're using multiple printers as well. So we're using everything from personal 3D printers that we had to the really advanced Ultimaker that had the dual nozzles, and a lot of those had different types of nozzles, which would affect the tolerances of and everything that we could print. And so we were able to scale up and scale down versions based on like how fast we needed to print, just to make sure that like, the methodology would work. And then when we discovered tree supports, it made it so we could print vertically, which was like a game changer for the print in place method that we wanted to do. And and then the printing in place is basically where you print it all as one assembly, and then you just break off those tree supports, and they'll be able to move already pre-assembled. And then this is some of the design progression in Cura when we were doing the slicing, different types of supports that we used. And so the left is the vertical, which we actually were having trouble adjusting the thickness. And so it would basically just end up as fusing the whole thing together when we couldn't get anything to actually fit together like that. The middle one is tree supports when we discovered them. Those are way easier to break off, and you can get in really strange angles that would actually make the print better, especially in the small slots that we had. And the same thing with our lower hinge, which is on the right. When it was laying down, the vertical supports would be way too thick, and we'd actually break off the entire round part there, trying to break them off.
For our materials, we ultimately decided on 3D printing because it's cost effective, it's got great tolerances, and we have limited manufacturing being at St. Martin's, and for us it's cheap and easy to prototype with. We decided on PLA because the nylon printing equipment wasn't working as good as the equipment that can print with PLA. On top of that, PLA is biodegradable, so where nylon's not exactly as biodegradable, PLA is a bit more. And we went through many trial prints with the PLA and the nylon wouldn't adhere on each layer as well as the PLA would, and that's what ultimately allowed us to settle on PLA. And again, for the spring, we went with Lee spring, and that's made out of music wire.
So one of the main forms of testing we wanted to do was vibration testing. We had a few options. They had piezoelectric sensors. They're not as accurate, but they do offer 4 in a pack, so we could have put them all over different areas. But again, not as sensitive. We could have used an accelerometer, but they were way too expensive compared to what we discovered, which was a geophone. And basically the way these work, they're usually used for detecting vibration in the ground. And all it is a coil that's over a magnet, a permanent magnet, and it's floating above it. And so, as we all know, when you put a coil over a magnet, it'll create an electric current. And so all we're doing is measuring the electric current that's coming off of the geophone. And so we would mount it. We basically take our server, we would mount it on the door, and then what we call the server floor, and we would basically open and close it and then measure the voltage, and that would give us an idea of the overall like it wouldn't give us the exact units for vibration, but it would give us a magnitude that we could measure, and then we could take the percentage of how much that magnitude is being taken down when we mounted our hinge. And so as you can see, the orange is when we had the hinge mounted, the blue is without the hinge, and this is just on the door because there was very little change in the server floor when we measured it there. And we mounted it using, as you can see at the top left, some tape, which worked very well. And yeah, so we had about, when we averaged all the values together, we had about a 29% decrease in vibration in the server door when we were closing it. Wasn't much of a difference, like I said, on the server floor or opening it. And so we also did a full finite element analysis, and we basically had to discretize the system and do the pre-processing and then do a solution phase. And all that breaks down to is you create basically an equivalent circuit like you see on the left. And since the material and length and width and all the material properties of all three of the springs were the same, we basically combined them into an equivalent circuit there. Then we had to find a governing equation, which we decided would be a derivation of Hooke's law. And then we divided it up into 3 different nodes. After that, we created equations using Hooke's governing equation. And we got those 3 equations you can see for node 1, 2, and 3. And then we put them into linear equations, and we created what's called global matrices. We then use those global matrices to solve for whatever we want, pretty much. But we decided the main thing was going to be deformation and stress.
And we modeled the spring at both the 180 degree and 90 degree orientations. The one pictured below is 180 degree orientation where the server door would be open. And so we modeled those in space claim, and then that would easily be translated over to ANSYS where we could add our boundary conditions and add our loads. And then we are left with the stuff like the graph on the right there. And this, when compared to the process that Alex described, gives us a good idea of how our springs are going to hold up and how they're going to handle the cyclical loading in the hinge.
Initially, we wanted to conduct some tension testing to record a variety of different print structures and ultimately save print filament rather than just continuously going through trial and error, although that's what happened. We wanted to test the different infill percentages. They go from anywhere from 0 to 100% and increase the duration of the print. So if you have something at 20%, it's going to take way less time than at an 80% infill. And same thing with the printing pattern. We were going to compare these. There's different structures of the infill, and it creates different geometries inside of the print. And we were going to use the tension test machine at the school to test a variety of infill percentages and printing patterns. We initially made some prints out of nylon, and again, our tensile test machine at school isn't working currently, so we were unable to conduct the tests.
And so this is the prototype that we use for all the testing. As you can see, we had the 3 springs on there, which actually proved to be way stronger than we thought. We also designed some fasteners, and we ended up buying those similar to the spring. We bought some stock screws that we just were able to use to be able to mount. On the bottom right is us trying to mount it before we had a spacer. So we actually had to print off a spacer and use that as well. And then this, you can go.
Yeah, this was me mounting the bottom part of our hinge into a vise in the manufacturing shop just to give it a strong support and allow me to actually put some pressure on the springs. And I took a fairly large piece of sheet metal and pressed on the back of it. And here I pressed pretty hardly, and I couldn't fold the springs a whole lot, as you can tell.
And like we mentioned earlier, with the print in place and being able to break away those tree supports, this was one of our main goals from the beginning. And once we discovered tree supports, we really wanted to figure out how to do this, how to print all the components together. It made there's no extra manufacturing that we needed. It was ready to go at this point. And using the design for manufacturing approach, this was the best way to go. And so on the top, you can see the tree supports there that were printed off, and that easily broke away after the print was completed. And so all that needed to happen was cut away those tree supports, and then you have a full functioning hinge. This operated super smooth, and you can see it at both the open and closed orientation there at 90 and 180 degrees. And so this was big for us. We weren't able to get the springs. We originally wanted to pause the print halfway and insert the springs where we had a full finished hinge there, but the tree supports made that impossible, and where we need to go back to the drawing board there. But yeah. And this is the CAD and Inventor files for our final prototype. You can see we dropped one of the springs there as it was just too much torque on the hinge. And we also had to thicken some stuff. So you can see the bottom hinge there in the red. We made the arms that go around the hinge rod thicker, because that's where we were breaking a lot during testing and after the print was complete. And so we also had to make a couple things thicker with the outside of the black hinge piece there around the rod. Just with the tolerance, like Alex was talking about earlier on the print nozzles, we just had to make that thicker so it had a better print quality.
This is our final prototype mounted into a box that simulates a server. We didn't want to drill holes in our test server that we got from IT, so we used a sheet metal box that was made. And on the left, it shows the movement of the top part, and that would be the door sliding back when you unlatch it. And then on the right, it shows as you would open, the hinge would go upwards, and as you close, it would force it downwards and allow it to move. This is our final design specification. This table just shows our spring specifications. It shows the leaf spring music wire, and our rod, upper hinge, lower hinge, and the fins are all made out of PLA.
And so our final budget was actually pretty much on par with what we thought it would be. We didn't know the specifics, but most of the budget went to actual like materials and testing. As you can see, 44% of it went to the geophone alone, about $75. But we actually only spent a total of $172.98. A lot of that's because we got a free filament, at least one roll from Ms. Davis in the school. And we also, a lot of the manufacturing services we had, whether it's from school or the Lacey Makerspace, were free. And so we had a remaining budget of $327.
And for our timeline, for the most part, we stayed on track time-wise. The bolded dates are our required assignments for senior design. And the hardest thing to stay on track on was the printing, because again, we just had tons of issues with quality and consistency of prints.
And like Austin mentioned, a lot of our roadblocks were having to do with the printing, and a lot of that was the prototyping and getting the quality, like he mentioned. Yeah, troubleshooting each of our designs. The nylon filament that we had access to was had absorbed the moisture from the air, and so we think that was why a lot of the prints failed in nylon. And so we needed a new roll or be able to bake off that moisture for a successful print. We also had a gap between the bottom edge to the server door, and so we needed to print off a spacer. And so this was an additional issue. We also needed to be able to move. We had to add the larger fastener holes that would allow for the movement of the server door opening and closing. The tension test machine was out of order, so we weren't able to conduct one of our tests on the different print orientations. And the issues with print in place were pretty lingering. Parts were fusing together, and so we just had to change some of the specifications on that print to get that to work successfully. And the leaking viscous fluid on the housing, we weren't able to include that, and so yeah.
And so we had a lot of stuff we could have improved in the end. The main thing was that when we were trying to do the printing in place, we had that set in our minds that we wanted to do that for our manufacturing method, and we would just slide those on halfway, as Finley mentioned. But the tree structure made that pretty much impossible. So if we had more time, we might have been able to figure that out. So for now, we have to basically print it all out individually and then glue the rod inside of there. We had a lot of printer malfunctions, and that's actually why we weren't able to have our final prototype with the springs on there for the mounting. Because the last ones we had, we actually broke all of our testing ones through the actual testing itself. And then we could have tested out the nylon probably earlier, and we wouldn't have had to deal with the scrambling to figure out the better material, which we ended up just doing the original one we had anyway, PLA. We also we could have used more time doing the viscous fluid dampening. Pretty much the leaking, we couldn't really figure out how to keep it inside the housing. And then adjusting the fit in the server. So if you were to look back at some of the video of the fit in there, it's slightly off, and that's because we've only fit the hinge in there a handful of times probably, and so each time the fit has been better and better. But especially when you have it moving up and down and side to side like that, there's a little bit of friction there until it actually, you need a little bit of adjustment there. And then we also needed slightly longer fasteners for the server, which would have helped with that friction as it's moving. I think that might have been because the sheet metal for the box that we made might have been a little bit thicker than the server, because we had measured it all out pretty well. And yeah, we think that if anybody else, any future groups were to do a part of this, to be able to build on our work and make something really, really good. And so see, these are some of the people and the organizations we wanted to thank. And these are some of our references. And if you have any questions, we'd love to answer them. Thank you.